All right, guys, here we go. So, second lesson for chapter 10. This is still part of section 1, but now we are just sort of doing the continuation here. So, a couple things we want to add in. You'll definitely see how a few of these things play into what we've already talked about here. So, one big idea for today's lesson is the difference between theoretical probability and experimental probability. So theoretical probability is the probability that you would normally think of. This is what you would expect to happen with certain events. So let me give you an example. If I were to roll a six-sided die 6 times, theoretically, I would get each value once, right? Because there's a 1 out of 6 chance that I would get a 1. There's a 1 out of 6 chance I'll get a 2. There's a 1 out of 6 chance I'll get a 3, on and on and on, right? So in theory, if I rolled a single die 6 times, I should get each one of those once, right? But we know that's not what would actually happen, at least not most likely, right? If we rolled a die 6 times, I most likely won't get one of each in my 6 rolls, right? I might get a couple 1s, maybe I get a couple 4s, whatever. So that's where experimental probability comes in. So experimental probability is what would happen if you actually conduct the experiment. If you were to, let me give you another simple example here. If I was to flip a coin 10 times, right, what would we expect the outcomes to be? What, in theory, what would happen? Right? Because heads is 50-50 and tails is 50-50, if I flip a coin 10 times, then of those 10 flips, 5 of the results should be heads and 5 of the results should be tails, right? In theory. That's the theoretical probability. But if I actually flipped a coin 10 times and actually conducted the experiment, it might be 5 and 5, but it also might not be, right? I might get 3 heads and 7 tails, right, or whatever. So I mean, it's possible I could get 10 tails on all 10 flips, right? Not likely, but it's possible. So anyway, the experimental probability is what would actually happen if you do the experiment. This is what you would expect to happen in any given case, is the theoretical. So that's kind of one of the main ideas. The other main idea for today is what we call a complement event. And this is the probability of something not happening. So that's like our key word right here, right, is the word not. So this represents a complement. The little A with the line on top, that little line represents the word not. So this is the probability of event A not happening. So real simple. Before I even explain the formula, let me just tell you in plain terms how you would do it. So if I said on a 6-sided die, and I'm going to just lay this out like this, right? So there's 6 results. So if I said, what's the probability of getting a 6? Well, we would say 1 out of the 6 cases is my probability of getting a 6. So 1 out of 6. So what then is the probability of not getting a 6? Well, if 1 out of the 6 is getting a 6, then the other 5 out of the 6, so the remaining values, fit this scenario of not getting a 6. So if there is a 1 out of 6 chance of getting a 6, then there is a 5 out of 6 chance of not getting a 6. What do those complement events add up to? Right? What is 1 6 plus 5 6? Right? It would be 6 6 or 1. So in probability, everything adds to 1. 1 is like the total possible result. It's like having 100%. Right, if in terms of percentages. In terms of fractions, the total possible is always going to be 1 for probability. So if there's a 1 out of 6 chance of getting a 6, well, if I subtract that from 1, then that tells me there is a 5 out of 6 chance of not getting a 6. So, and that's what you're seeing in this formula right here. So if I ever want to find the complement event to something, I just take my fraction, subtract it from 1, and get the complement event. That also works with decimals. So if I had a decimal, like let's just say instead of a fourth, what if you had 0.25, right, as my probability? So if I did 0.25 was the probability of getting something, then 1 minus 0.25, which would be 0.75, would be the complement event. That would be the probability of not getting that outcome. Works great with some of the bigger problems like this as well. In fact, it can become a great shortcut. We already talked about in the last lesson that there are 36 possible outcomes when you toss 2 dice, right? And so if we said, this was an example I gave in the last video, what's the probability of getting doubles? Well, 1, 2, 3, 4, 5, 6. So 6 out of the 36 is my probability of getting doubles. What's the probability of not getting doubles? Right? Well, that would be all those remaining dots, which you could count them if you really wanted to, but this formula is a whole lot quicker, right? The probability of not getting doubles is much easier to say 1 minus 6 out of 36 and getting the complement this way. And if you just think of it in kind of plain mathematical terms here, there's 36 results, right? So if 6 of them are doubles, then the other 30, right, the remaining 30 out of the 36 would be the not doubles, right? It'd be everything else. So anyway, that's kind of one of our biggies for today. So let me take you to the next page. So some of this I already have pre-written out here just to make it go a little quicker for you. So we're looking at the pink ones today. So just to take you back to something that we talked about in our previous lesson as well. If I were to flip 2 coins and I said, what's the probability of getting 2 tails? Here's what we showed in the last video. Here's what a tree diagram looks like. So you can see there are 4 possible outcomes when I toss 2 coins, right? Well, one of those 4 is the probability of getting 2 tails, right? And so I can see that real easy with my tree diagram. I could do it with a lattice diagram. So this heads and tails represents one coin, this heads and tails represents the other coin, right? And so I could get heads heads, I could get heads tails, I could get tails heads, or I could get tails tails, right? And so with the lattice diagram, again, I can see there are 4 possible results, and one of those 4 fits that description, right? 1 out of the 4. So lattice diagram is a great way to go. We can also use formulas for a lot of this kind of stuff, and we'll talk about some of that later. So if there's 1 out of 4 chance of getting 2 tails, what's the probability of not getting 2 tails? Right? So if 1 out of the 4 is 2 tails, then the remaining 3 out of the 4 would be not getting 2 tails. Right? And so here's just putting to use today's formula to see it as well. So I could do it with a tree diagram like this. I could do it with a lattice diagram. I could also do it with a formula. Right? And so there's like many different ways, many tools that we have to doing things like this. It's just a matter of whatever tool is working best for you for that scenario. Obviously, when it comes to something much bigger like a deck of cards, I don't want a diagram for a deck of cards. There's too many, right? 52 is too big. Right, I don't want a diagram for that. There's too many results. So this is where I really want to draw on formulas and things like that. So if you're not familiar with a deck of cards, it might help you to pull up maybe a little image of a deck of cards, and you can see them all. But basically there are 52 cards. 26 of them are red. 26 of them are black. There are 4 suits. Right? There's diamonds, clubs, hearts, and spades. In each suit, there are 13 cards. So there's 13 diamonds, 13 hearts, so on and so on. So anyway, from our deck of cards, if we were to say, what's the probability of just reaching in and pulling a queen? Well, there are 4 queens in a deck. So 4 out of the 52 are queens. So if we said, what's the probability of not getting a queen? Again, keep in mind there's 52 cards. So if 4 of them are queens, then the remaining 48 out of the 52 are not queens. Right? And so again, that's kind of our key one for today. And then one more thing I want to show you. So take a look at this one. I'll try to get all that on the screen for you. Okay, last one. So there was a spinner, right? Spinner had numbers 1 through 12 on it, right? And they're all equal probabilities. So 1 out of 12, 1 out of 12, 1 out of 12, so on and so on. if we spin a spinner 180 times, what would you expect the results to be? In theory, what's the probability of how many ones you would get? What's the probability of how many twos you would get? Threes, fours. So if these are all equally likely to happen, right? So then I'm going to get this 1/12 of the time. I'm going to get this 1/12 of the time. 1/12, 1/12, 1/12. So if I did this 180 times, well, 15 out of those 180 should get this, because that's 1/12. 15 out of 180, 15 of the times I should get a 2. 15 of those times I should get a 3. So again, these are all 1/12, right? If you reduce the fraction, it's 1/12, right? And so that's what I'm expecting to happen. This is what theoretical probability says should happen, right? Is I should get these guys equal amount of times. So I took that 180, I divided it by 12 and got that 15 right there, right? So it tells me that each of these should come up 15 times each, in theory. But we know that if we conducted an experiment and we actually spin this spinner 180 times, right, this is probably not going to happen, right? And so what they did was they actually conducted an experiment where they did that. They spun the spinner 180 times. These are the results. So 13 out of those 180, they got a 1. 21 times, they got a 2. 22 times, they got a 3. So you can see all these values down here, right? This is what actually happened in the experiment. So this is experimental probability. This is theoretical probability, right? That's the difference. So if we said, what's the theoretical probability of getting a 4? Well, in theory, I should get it 15 out of the 180 times, right? But in the experiment that was conducted, what actually happened? So the experimental probability of getting a 4 in this case was 20 out of the 180, right? And so that was the difference in this event. Obviously, the outcome would change if you kept doing this. But in this event, that was the difference. So this was what should happen in theory. This is what actually happened in the experiment. So one of the questions you're going to get is, which one of these values had a case where the theoretical probability and the experimental probability matched up, right? Because that is possible. That could certainly happen, where my theoretical and my experimental line up to be the same answer. So if you look at number 9 right here, notice that 9 showed up 15 out of the 180 times, right? And so here's a case where the experiment actually matched with the theoretical, right? And so that's a question you're going to run into down the road. So I wanted to point that one out. But that is it for part 2.